afternoon. Welcome to my session on how Canva uses Snowflake for data lifecycle management. In essence, how to safely and responsibly delete production data on Snowflake. But before I begin, you may be wondering why I am speaking to you in English, considering my very Korean-sounding name. 안녕하세요. 제 이름은 김규상이고요. 캔바에서 일하는 소프트웨어 엔지니어입니다. 근데 제가 호주에서 태어나고 호주에서 살아서요. 제 한국말이 좀 약합니다. 하고 양해 부탁하겠습니다. 그것 때문에 이 프레젠테이션은 영어로 진행할 건데요. 뭐 끝에서 아니면 세션 끝 이후로요. 질문 같은 게 있으면요. 한국어로 할 수 있으면요. 하겠습니다. 노력을 하겠습니다. 감사합니다. So, once again, my name is Kyu-Sang Kim, and I am a software engineer at Canva. I was originally part of the warehouse platform team for the context of this presentation, but I have since moved onto the privacy engineering space within the trust and safety area, which complements what I'll be talking about today, actually. Before we get into the content, I would like to do a brief overview of the presentation agenda today. First, I will do a quick overview about what data lifecycle management is and the issue that it presents. I assume most of the attendees are quite familiar with this topic, considering the session type, so I will not go into too much detail. We'll then talk about the existing work in this space to better understand how this issue has been approached in the past, before moving into what I hope many of you are here for, a novel policy-based time-to-live technique built on Snowflake, which I'll be presenting to you today. However, a new technique is meaningless for an enterprise company without scalability. So I'll then talk about how we support PTTL at Canva scale and how we assess its performance in meeting our objectives. Finally, we'll wrap up the presentation with the lessons this project has shown us and what we see as opportunities for the future. So, for those who are unaware of Canva, Canva is a global online visual communications platform on a mission to empower the world to design anything and publish anywhere. It's a simple way to create beautiful designs, from presentations such as this one, to infographics, videos, t-shirts, websites, and also social media graphics. Canva launched in 2013 and is based in Sydney, Australia, with multiple remote offices across the world in the Americas and Europe as main overseas hubs. We have more than 190 million monthly active users, with 85% of the Fortune 500 embracing Canva to bolster their productivity and achieve their goals. That being said, I think it's more important to talk about the scale of data that we work with at Canva. We currently host at least 27 petabytes worth of data on Snowflake alone, which is growing at an exponential rate. To kind of give a comparison, this number was only 20 petabytes 3 months ago. We have 483 contributors in our data warehouse code repository, looking after more than 15,000 dbt models over more than 29,000 pull requests. In short, there's a lot of data we need to manage. This brings us to the first topic of today's presentation, data lifecycle management. I'll do a quick overview and what we're focusing on today, data disposal. As aforementioned, I've assumed that most attendees are familiar with what data lifecycle management is and how it works. At a glance, there are 4 points: creating, storing, using, and finally, disposing. Today, we are going to focus on disposal. When I mentioned safely and responsibly deleting production data earlier, the first thing that comes to mind for most engineers is it's really hard to do correctly. But why is it really hard to do? So why do we need to dispose of data in the first place? First of all, storing data costs money. And having a lot of data, 27 petabytes or more, which for most people is a mind-boggling number already, means it's going to be very expensive. Second is compliance. Data stored with no business purpose could be a compliance risk, depending on the local laws and regulatory requirements in which your company operates. And finally is confusion. Needlessly stockpiling data could lead to a confusing experience for your data scientists and stakeholders. You may have data that is outdated, which shouldn't be used by scientists, but they may not always be perfectly aware of that requirement. Now that we know why we need to dispose of data, why is it still so difficult? To start, data is a very valuable asset. At Canva, you could say that data is one of our most valuable assets, and losing it would negatively impact our operations significantly. Second, it's irreversible. When we talk about the disposal of data, we're not talking about taking data from someplace and storing it someplace else. We think the disposal of data means the destruction of data, which is an irreversible action. You cannot undo this. This leads to our third point, which is the downstream effect of any unintended disposal. If we make a mistake and delete important production data, it could lead to a massive amount of data loss, but more importantly, it's a big risk to company reputation. Imagine you've used Canva to store an important design for work, which you've worked very, very hard on, and it just suddenly disappears. Would you still come back to Canva? But worst case scenarios aside, let's talk a little bit about the existing work by one of my colleagues, Gino Yama, a senior analytics engineer at Canva and also a Snowflake data superhero. His original blog about a time to live, or TTL technique, served as the foundational inspiration for me and the team to take on this endeavor. So, what was it about? As a general overview, the technique is actually quite simple, but allow me to drill deep on what makes this a little bit more special. It's these tags on the tables. What each of these tags do is that they can store a key value pair. In this case, let's imagine that in the tag for this table, I store that the table's TTL is equal to 6,000. We can put different tags on different tables and have a separate procedure designed to operate on each of them. From that procedure, we can have a task that will call the procedure at a certain schedule. In this case, the TTL procedure will drop tables depending on a table's TTL value. As an example, let's imagine that the current time is 7,000 when the TTL procedure is executed by the task. Table 1 at the top has a TTL value of 9,000, while table 2 at the bottom has a TTL value of 6,000. The TTL procedure, given that the timestamp was 7,000, will keep the first table at the top, but will destroy or drop the second table at the bottom. This pretty much summarizes the entire idea of time to live. Now, what were the key takeaways of this technique? Well, first of all, it is simple and intuitive. Most of your analysts and engineers could take a look at this technique and immediately understand its purpose. It's also great for cleaning up scratch tables. If your analytics engineers or data scientists are working on scratch tables and the costs or data hygiene is becoming unmanageable, this technique allows you to drop tables automatically after a specific amount of time, rather than dropping entire schemas or databases all at once. However, it is not all good news. There are some weaknesses of this TTL technique. First of all, it lacks granularity of control beyond the table level. The technique will allow you to delete the whole table, but it might not necessarily meet your needs to do that. Second, what if the condition for deletion is not temporal? TTL, or time to live, per its namesake, is a technique that relies on time as a condition for keeping or deleting data. Finally, scalability. This one is debatable depending on whether you are willing to invest the time to build a framework for this technique. But as it currently stands, with no supporting framework, TTL is not very scalable, as you have to manually set and apply the tag values, which severely restricts viability when you have thousands to tens of thousands or even more tables to work with. If you'd like to read more about Gino's TTL technique, here is a QR code and a URL which links to Gino's original blog post and goes into a lot more depth than I have time for today. This brings up the main topic of today's presentation, which is about policy-based time to live, or henceforth I will refer to as PTTL. First, I want to talk about the core underlying technology behind PTTL, PTTL would not be possible without Snowflake Row Access Policies, or RAPs for short. What are row access policies? In a nutshell, considering the name, RAPs filter rows returned in a query based on conditionals that you can set either arbitrarily or in accordance with certain business logic. Let's imagine I have a data analyst here, and this analyst is only permitted to see data after including a timestamp of 100 seconds as an arbitrary restriction. Here on your left, I have a table with no row access policy. In this case, there are 3 rows, A equals 0, B equals 100, and C equals 200. The second column is referring to T in this case. On your right, I have a table with a row access policy. It has the same content as a table on the left, but in this case, you can see that the first row has been grayed out or made transparent. You can't see it. That's what the row access policy allows us to do. Is that instead of the analyst seeing data that they shouldn't be seeing on the left with respect to row A, they can only see the data on the right, which is the bottom 2 rows, B equals 100 and C equals 200. Our analyst cannot see A is equal to 0 row. Row access policies are very versatile in that we have options on how we want to filter rows. We can go with a simple approach by filtering based on a certain row attribute, like what we just saw with the analyst example. I don't have time today to discuss the more complex approach by filtering on mapping tables, but I'll be happy to take any questions either at the end of the presentation if time allows, or after this presentation outside. For now, let's formalize the simple row attribute-based filtering with a code example of the earlier analyst scenario. You may notice that the wrap looks very similar to a standard Boolean UDF, or user-defined function. Many of you, may be confused about right now. What has row access policies got to do with time to live? All I've shown you so far is filtering and hiding data rows. I haven't showed any deletion or anything resembling it. This leads to a question the team had when we were first researching how we were going to do this project. Does a data row exist if nobody can see the row, like Schrödinger's cat? I like to think that I said this because I used to have an interest in quantum physics, but my colleagues tell me that it supposedly wasn't me, and they're only 50-50 on it being actually me without a recording. I can't tell if that's an allusion to the cat or if they're being serious, but the point still stands. Has the data been deleted if nobody can see it? This is the basis from which our policy-based time-to-live technique is built. PTTL is a 2-step solution which allows you to safely and responsibly delete data. Step 1 of PTTL is to first make unwanted data invisible to users via a row access policy. Those users could be your analysts, or could even be a build tool, such as dbt. Step 2 of PTTL is to take the hidden data and destroy it at a designated time of your choosing, whether that is monthly, weekly, daily, hourly, and so forth. We call step 1 of PTTL a soft delete, because we haven't actually deleted anything, and it's only being hidden from your users. However, from the user's perspective, they are unable to tell if the data has been deleted or not. But step 2, hard delete, because we are actually destroying the data from the table and we are unable to recover it. Yes, we are aware that there are features such as Snowflake time travel, but I'll be happy to address any questions regarding it after the session today. But since that, now what would a table with PTTL look like? First, let's imagine we have this original pre-existing table containing some production data in our warehouse. By applying PTTL, what you can do is split the original table data into 2 separate sections, or buckets, as we like to call them. The section at the bottom is the wanted data, which is data you consider to be valid and allowed to be used by your data scientists. There is also another section at the top, which is unwanted data that you consider to be invalid or out of policy and should be removed from the table at the earliest opportunity. The really nice thing about PTTL is that for your users, each of the row access policies are refreshed at query time, which ensures that your user is only able to see data that is specifically permitted by the row access policy for every single query. For example, if I query the table from earlier and returns me 3 rows, if one of those rows expires according to the attached row access policy, my next query to the table will only show 2 rows automatically without any manual intervention from the user or a warehouse administrator. That pretty much explains how the soft delete works. As you've now separated the table into 2 sections, wanted data and unwanted data, we now need to consider how we delete the data at the designated time. Another benefit of row access policies is that if you closely examine the official documentation, row access policies allow us to determine which rows to return for both select and delete statements. Please note, in particular, the latter half with regard to delete statements. Let's return to the old analyst example once again. What would deleting rows from a table with PTL look like for an analyst who wants to clean up their table? In this case, let's imagine they want to delete the entire table, and the row access policy only allows them to see wanted data. When the analyst runs the deletion command, in accordance with the documentation, only the wanted data gets deleted. However, the unwanted data that the analyst cannot see is still there. It still exists, but since the analyst cannot see it, the analyst perceives the table to be empty. This leads to a bit of a realization. What if we invert the condition for a service user? In this case, what would happen is that the service user, unlike the analyst, cannot see the valid data or the data we want to keep, but it can see the data that we don't want to keep. If we use the exact same delete command that the analyst used as the service user, who can only see the data that is unwanted, in accordance with documentation, the unwanted data becomes deleted. Once again, in a similar fashion to the analyst, the service user considers the table to be empty from their perspective, but the wanted or valid data that the service user cannot see still exists. To summarize, if we have a table with PTTL and a cleanup has been performed by a service user, the data that we consider unwanted or out of policy has been cleared away, but all the valid data that we want remains untouched. This concludes the hard delete step and also the PTTL process as a whole. Now that we're equipped with an understanding of what TTTL and PTTL is, what are the differences between the 2 techniques? First things first, only whole tables could be deleted with TTTL. However, PTTL provides you additional granular control with the row access policy to target specific rows within your table to be deleted. That then brings us to our second point of comparison, which is TTL mainly handling temporal conditions only. You could theoretically expand the tag-based process of TTL to support more conditions, but with PTTL, it's easier to handle arbitrary conditions right out of the box. Finally, although I declared TTL to not be very scalable earlier, if you take a look at the PTTL technique alone right now, you may be wondering that we haven't really solved the problem of scalability just yet. So let's take a look at how Canva supports PTTL at scale. When I originally spiked the concept of PTTL to the team and our stakeholders, many had concerns on the use of row access policies for PTTL, which need to be addressed before we committed further to developing it. Chief among the concerns from our data engineers was how query performance might be perfected by tables utilizing row access policies for PTTL. Next was questions on how we would apply and, more importantly, enforce PTTL on tens of thousands of tables. We considered not only where Canva is right now, but also with its data needs, but also into the future with our exponential growth in data use. Finally, and most importantly for some of our stakeholders, how will we have visibility over the use of PTTL at Canva? When we performed our initial analysis of the first point about query performance, we ended up with some surprising results, as shown in this graph, particularly in the higher row counts. To summarize the graph, we discovered that query performance was negligibly affected for tables between 10 and 100 million rows. We also saw that larger warehouse sizes reduced query times on tables with a row access policy. And finally, we observed that the table metadata operations, which are optimizations made available natively by Snowflake, were slower, but they were deemed inconsequential for Canva's use case. With that, our first concern of quick performance for PTTL at Canva has been adequately addressed. We now move on to the second concern of scale in how we will apply and enforce PTTL to tens of thousands of tables. Manual application of PTTL will not be an effective use of time and resources as it could be prone to mistakes. Instead, Canva has taken on an automated approach by developing an in-house support framework that we call the PTTL platform. This is a high-level architecture diagram on how we achieve the first step of an automated application of PTTL, or soft delete. Let us start by breaking down this diagram into its two major sections. First, we have the Snowflake database where all our tables are stored. In order to focus primarily on how the soft delete is applied, please assume that the veracruz policy definition in relation to a predefined PTTL policy has already been made available in the warehouse. For example, when you roll out a new business policy. Second is the Python-based PTTL platform, which the automation is managed. At Canva, we use dbt to orchestrate and build our data models to Snowflake. To minimize friction to our users' workflow and experience with dbt, we've made it possible to configure which PTTL policy should be applied to which table directly in our dbt model configurations. The PTTL platform allows us to take advantage of dbt artifacts, such as the project's manifests, which we pass to load an understanding of the dbt project into the platform. The loaded information is then passed to the handler, which will then retrieve information from a target table, such as whether a PTTL policy has been correctly applied. In this example, let's assume that our table does not have a PTTL applied, but its dbt configuration dictates that it must have the one that we defined earlier. At this point, the handler would recognize that the table is missing the necessary veracruz policy and begin automatically reapplying it. The handler achieves this by issuing a command to the warehouse to apply the correct veracruz policy to the target table. Unfortunately, we can still see that this is still a manual process that requires someone to manually run a terminal command. To achieve true automation, we can use Kubernetes to package and run the PTTL platform to a certain cadence via a cron job depending on your needs. That covers soft delete nicely, but we still need to address how we do hard delete automatically. What I really like about the design of our platform here is that not much extra code is required to deliver this functionality. The process remains mostly the same, but instead of the handler issuing commands related to soft delete, we can instead change them to hard delete. As we saw from the previous slides, the veracruz policy will still manage what the PTTL platform handler can see as a service user, and as a result, control what it can delete. As a result, when the handler issues a delete or drop command, only the unwanted data from the table will be cleared while leaving the wanted production data untouched. For additional safety, we also apply the same conditions defined in the veracruz policy to filter only the accepted rows, even if the policy were to fail unexpectedly, as unlikely as it may be. This resolves our second concern for PTTL, where we're now able to apply and enforce PTTL at scale. Finally, we need to address our last concern, which is how we will have visibility of a PTTL at Canva. This is particularly important as some departments would like to know how many tables have PTTL defined and other metrics. We achieve this by logging an event to a separate PTTL event order table on Snowflake whenever an action is performed by the PTTL platform. Using these metrics and these events, we can create metrics from which easily tell in a report like the metrics that were desired, such as how many rows were deleted in a table. With that, all three concerns for PTTL have now been addressed. Once again, we return to the early comparison of TTL versus PTL. We've covered the first two, but I have shown you that PTTL is now scalable. At Canva, we care deeply about continuing to safely and responsibly delete data, which leads us to identify learnings that we've had throughout the journey of this project, and also uncover opportunities for the future. One of the first lessons is that PTTL is viable in lieu of a native solution. PTTL has made it easier to translate business rules and objectives into concrete technical implementations. Our approach to PTTL has minimized friction and impact to our data consumers, such that our users have little reason to notice that PTTL is occurring in the background. And finally, and most importantly, PTTL has increased the level of confidence in data stored within our Snowflake data warehouse. Our users can be confident that the data that they can see on the data warehouse is what they're permitted to see and work with. However, with those lessons came opportunities for the future of PTTL. To start, is a Snowflake native solution. When we discussed our new PTTL technique and platform with our wonderful support and sales team in Australia, they have worked with us in collecting requirements for a native solution and introduced us to the right people at Snowflake to explore these new ideas. I don't have too many details at the moment, but something exciting might be coming to private preview soon. In particular, we want to minimize policy latency. From the early presentation slides, you may have noticed that if the policy config is set on DBT at X time, what happens until Y time when the soft delete is scheduled to run? We want to minimize the latency gap as much as possible. Finally, this presentation has shown that the way we have been using regex policies is not intended, well, mostly, to support our automation efforts until the Snowflake native solution is ready. We've been working with the Snowflake engineering team to help support our work in continuing the automation to improve the efficiency and maintainability of the PTTL platform. Before we finish the session, and particularly, I don't have time for questions. I'd like to thank the team who have worked hard on this project, and also all the other engineers who have worked really hard to accommodate the introduction of PTTL at Canva. Thank you, everyone, for coming to today's presentation. I hope this presentation has showed you a little bit about how we can approach deletion of production data on Snowflake in a safe, responsible manner which can be trusted by your engineers. Thank you.